Welcome everyone to this IVM seminar. Today we have Alexey Bogdanov from the Weizmann Institute of Science. So a brief summary of his scientific career. So Alexey started in Moscow, where he got his PhD in 2013, and he just told me a few minutes ago that he got in touch with EPR pretty soon, doing photochemistry on liquid crystals and using spin labels to figure out the orientations of these molecules. And then he stayed in Moscow as a scientist till 2022. Was a pretty successful stay because he got in 2022 he got the Emanuel Medal from the Russian Academy of Science. And then this propelled him to go to Weizmann Institute of Science with Daniela's group, where he started in 2022 and is still there now, and also a very successful stay because in 2024 he got the Young Investigator Award from the International PR Society. So today is going to talk about gadolinium hyperfine spectroscopy, actually, with the gadolinium complexes. So Alexey, the floor is yours. Thank you.
Okay, Thomas, thank you very much for the introduction, and all the other organizers of this meeting. Thank you for invitation. Thank you for organizing this. And so let's turn to the science. So I will be talking about how we use the Endor spectroscopy to determine the orientation of the zero field splitting tensor in gadolinium chelates and gadolinium complexes. So how we try to do this, and how we apply this to structural studies on biomolecules. And this is somewhat a project in the making, so I will still leave some questions unanswered. But well, let's turn to the essence of the project. So, okay. So for the long time, in the beginning of EPR, of the spin labeling, the nitroxide spin labels were the sole actors on the stage, and they have been thoroughly studied. They have been around since the 50s, since the 60s, and we know a lot about them. And actually, recently, the repertoire of the available spin labels has been broadened to include other stable radicals like tritiles and the metal complexes like copper, manganese, and gadolinium. Here in Daniela's lab, Weizmann, we do a lot of studies on gadolinium complexes. So these are our main actors. It's a high spin system. It has a spin of 7.5, and this provides us with several advantages over the standardly used nitroxide spin labels, such as, well, for example, because of the high spin, they have the intrinsically high sensitivity toward the microwave. And also because they relax faster, they have fast relaxation, so it allows to faster acquisition and go in lower in temperature, which also enhances the polarization. Of course, the temperature also can be, the fast relaxation can also be a drawback, but okay, let's not focus on that. Also, the gadolinium spin labels have narrow central transition on of the spectrum, which narrows when the field gets higher, so it scales with the square of the spectrometer frequency. So it's nice to work with them at high field. And apart from that, these spin labels possess very high biocompatibility. They are resistant to reduction in the in vivo, in cellular media. So actually they are being actively used as the contrast agents in the MRI in vivo. Well, of course, with these advantages come the technological challenges that we have to work at lower temperature, and it's easier and it's more beneficial to work at higher field. But since if we get through this technological challenges, then we gain a lot. And when we look on the spectra, the EPR spectra of gadolinium spin labels, so the main anisotropic contribution to the gadolinium spin Hamiltonian is, of course, the zero field splitting. So the zero field splitting is the splitting of otherwise degenerate spin states corresponding to different electron spins, even in the absence of the magnetic field. And it arises from by several mechanisms, by the dipolar interaction of the electrons, or from the spin orbit coupling. And the usual zero field splitting Hamiltonian is written out like this. So it has the axial part proportional to the axial part D, and it has the rhombicity part. So when we're talking about gadolinium, then the zero field splitting of gadolinium is pretty small. Well, if you compare it to the zero field splitting of other lanthanides, or if you express it in the units of energy. So the magnitude of the zero field splitting interaction in gadolinium is on the order of a few hundreds of megahertz to gigahertz. So in energy scale, it's not very big, but for the EPR spectra, it's quite a lot. So the reason for this is that gadolinium has a half-filled F shell. So the ground state doesn't have any orbital momentum, so there is no first-order spin order coupling. So most of the zero field splitting effects come from the second-order splitting second-order spin orbit coupling. And so the ligand field perturbs the orbital momentum, and this is and then the spin orbit coupling produces the zero field splitting. And a few words why we are interested in it at all. So first of all, of course, as spectroscopists, we are interested in the zero field splitting, how it influences the spectra, how it influences our sensitivity through the spectral width, how it affects the relaxation time, which affects the possibility to measure something. And also, this is what will be talking about, is it also can be used as a source of structural information about the anisotropy of the interactions. And of course, it's important also for MRI of these spin labels of these contrast agents, gadolinium-based contrast agents, and of course, it should be important for some applications, both in the quantum information science and with the use of the magnets. But from what I have said, also the theoretical prediction of the zero field splitting of gadolinium is still poor, because it's very small. It's really very difficult to calculate. So by providing the experimental information about the zero field splitting of gadolinium, we also can have the valuable benchmark for the theory. So once the theory, the ab initio approach to them appears, we can test it on the information that we have. So what do we want to do? So, okay, so in this work, we set a goal of determining of the orientation of the zero field splitting tensor in gadolinium chelates, and explore the ways of using this orientation as a structural tool. So let me explain what I mean. So if we look at the EPR spectrum of gadolinium chelate, looks something like this. So like here, the black spectrum is the experiment and the red one is the simulation. We see that in the center, there is this central transition, which is the transition of the electron spin from -half to half. It doesn't depend to the first order of the zero field splitting, so it's very narrow. And then there is this broad blob, which doesn't have any structure, which is attributed to all the other transitions. And the reason for such a featureless spectrum is actually the distribution of the zero field splitting parameters. So let me show you it like this. So gadolinium is the atom in the center, and it is surrounded by ligands. And the ligands, they create the ligand field around it, and then through the spin-orbit coupling, they create the zero-field splitting. But the gadolinium does not does not direct the positions of the ligands around it, unlike the transition metals, because the f orbital is pretty much spherically symmetric, so it acts basically like a sphere of the positive charge around, and then the ligands are kept around it by the electrostatic charges, and they can actually freely move around. So then the ligand field is fluctuating, it's transient. And this leads to a very broad distribution of the zero-field splitting parameters, of the zero-field splitting magnitude, and probably also to the distribution of the zero-field splitting axis. So usually, to simulate such a spectrum, we need to assume some shape of the distribution of the zero-field splitting parameters. So usually, the standard way is when you take a Gaussian or a few Gaussian distributions, usually you take a positive and a negative Gaussian distribution of the D parameter of the axial zero-field splitting, and some form of the distribution of the D over E. And the good thing about this formulation of the zero-field splitting parameter distribution is that here we can assume that the E over D is always smaller than 1/3, and it means that the principal components of the zero-field splitting tensor are ordered in a special way. So this thing is the convention, like how we are used to doing this. But actually, there is an alternative formulation of the zero-field splitting parameter distribution. So we can actually have a Gaussian distribution of the D parameter and the Gaussian distribution of the E parameter. We can make them independent. And basically, it would mean that all of the parameters of the zero-field splitting tensor, they have the 3 Gaussian distributions. So what is good about, so what is bad about that? That we no longer comply with the standard, with the standard assignment of the axis. But what is good about that is that actually there can be a situation when the positions of the axis of the zero-field splitting, well, here I show them x, y, and z, they're pretty much fixed in space. So the magnitudes of the zero-field splitting principal values, they fluctuate, but the orientations stay more or less the same. And this is the basic hypothesis that we have in our in this work. So because the geometry of the ligands, it changes, but it does not change completely. So because the chelate has the structure, the chemical structure that keeps it together. So then we may assume that the orientation of the axis of the zero-field splitting is not completely arbitrary, but it has the certain, like the certain maxima. And then the main thing that fluctuates is actually the values, the principal values of the zero-field splitting. So and then the handle that we have to measure this geometry is actually the Andor spectra. And so this is actually what we see in the experiment. And so now let me explain to you a little bit about how we measure it using this Andor spectroscopy. So first, consider just the regular Andor experiment. So we have the 4-level systems. If we have a spin-half, electron spin-half system and the nuclear spin-half system, so then we have a splitting due to all the interactions that we have. We have a 4-level system with the 2 NMR transitions, which are allowed NMR transitions, the alpha and beta, that appear around the Larmor frequency of the nucleus. And of course, because of the hyperfine interaction, it is angular dependent, so it depends on how the electronuclear dipole is directed in the magnetic field. It also gives rise to the powder pattern. So here we just consider the case when where the hyperfine interaction is purely dipolar, so we don't have the isotropic part. Of course, you can include this, but this is not important for us. So then we have a powder pattern which has these 2, let's say, prongs, 2 shoulders. The one of them for the electron spin of +1/2, and the other one for the electron spin of -1/2. And so they give rise to this to this spectral shape, which we usually measure using the MEMS, the pulsed MEMS Andor. And I just remind to you the pulse sequence for this. So this is a double resonance technique. We use the pulses both at the microwaves that are applied to the electron spin and the radio frequency field, which is applied to the nuclear frequency. And so, like here, we basically create the correlated spin polarization state using a couple of 90-degree pulses. And so then we partially destroy the state in the case where we have the RF pulse, which is in resonance with the NMR transitions, with the Andor transitions. And so when we have the resonance, when we hit the resonance, it actually makes this spin echo a bit smaller. And then, of course, in the detection, we can use the CPMG detection to obtain more signal, which is very beneficial. So this is the spectrum that we have. So if we don't have any RF, then we have some intensity of the spin echo. But when the RF hits the resonances, then we see that the spin echo becomes smaller. And here we can easily recognize the powder pattern. But also, because we're using this MEMS Andor technique, we also have to take care of the blind spots. It's also very well known. So the thing is that the maximum Andor efficiency is observed at a certain combination of values, a certain combination of values of tau and hyperfine splitting. And basically, it means that to assess the long distances, we need to it means that we need to measure the smaller hyperfine splittings, and then we need to work with longer tau. So we have some relaxation restrictions. So we are doing the fluorine Andor. This technique was pioneered by Andres Meyer and Mariana Benatti in 2020, and since then there were a lot of works related to this technique. And the advantages of using the fluorine are, of course, the very high sensitivity due to the high nuclear gyromagnetic ratio of fluorine, so we can measure the long-range distances. It has great specificity because fluorine is almost absolutely absent from all the living systems. And also a nice bonus of working at the high field is that the fluorine Andor signals are well separated from the proton signals, although at lower fields we can also work, but we have to take care of the overlapping proton resonances. So, and then usually when we work with Andor in EPR, the lines are really very broad. So by EPR excitation, almost never we excite the whole spectrum. Usually we excite a portion of the spectrum, a portion of here, a portion of a orientation pattern. And so it means that the electronuclear pairs that we see at this excitation, they are not all possible electronuclear pairs, but only those oriented at a specific angle. And this gives rise to the effect which is known as the orientation selection. So basically, if we look at the standard nitroxides that we use, so it has the G values, X, Y, and Z. They have resonances, EPR resonances at different field. And so depending on where we sit in the field, on which of the orientations of the nitroxide we excite, so this is regulated here by these angles phi and theta. So we excite different orientations of the electronuclear pairs with respect to the field, and this is the angle beta. And so what is interesting to us is, of course, these structural angles gamma and rho, which defined the transition from the hyperfine frame. So basically how the fluorine atom is oriented relative to the G frame. And the G frame, we know this orientation because we know everything about, for example, nitroxides. We have been studying them for a long time. And this is how it works. So for example, when we're sitting at different positions, at different positions of the nitroxide spectra, and we record the Andor, And the Anders spectrum shape depends on where we sit. For example, here at the position A, here we excite this portion of the spectra, which is generally relates to the GX axis. So it means that we mostly excite the nitroxide radicals for which the x-axis, the NO axis, is oriented parallel to the magnetic field. And here you see that we excite mostly the parallel part of the powder pattern. And of course, we can simulate it and we can determine actually the mutual orientation of the nitroxide fluorine vector in the principal system of the G-tensor. So let's see how it works for the gadolinium labels now. So this is in principle well known. This has been done for a long time previously. So, but what do we have with gadolinium? So the first thing when you think of when starting to use the gadolinium spin labels is you try to use the central transition, the transition from the electron with the ms from -half to half. And basically this transition, it acts as a quasi spin half system. So it gives rise to a doublet around the Larmor frequency, everything as usual. And of course, in the presence of the different orientation, we have the powder patterns. And these powder patterns can be used to get the distance information. It was first done by in the group of Nick Cox in Australia, and also in the work of Manash here. We used a series of spin-labeled proteins. The proteins labeled with the gadolinium spin labeled, and depending on the distance between the gadolinium and fluorine in these labels, we got the different splittings. So from the highest to the lowest. So with the lowest part, we actually didn't see any splitting. And they agree very well with the distances that we obtained using the NMR. With the same samples, we can do the PRE experiments, how the gadolinium enhances the spin relaxation of the fluorine in solution. But then we had another idea. What if we go outside of the central transition and we go to the transitions which are like the satellite transitions, the transition with a high spin? And so what happens here is that when we observe at the transition with a different m sub s, it shifts our line. So this is a doublet that we would observe at the central transition. And if we go to this one or to this one, to +5½ +7½, then they all shift. So we still observe the same doublet, but it will be shifted with respect to the Larmor frequency. And if we are working on the 5½ sorry, then we have it them here or here or here. So basically, each of the transitions, excitation of each of these transitions gives you a doublet anywhere else. But if we make one more step and consider the PAPE pattern, then it gives us additional advantages. So namely, so imagine that we work at very high field and very low temperature, and the only excitable transition, like everything is frozen out to the lowest line, APR, -7½ -5½ transition. So then, because the hyperfine splitting, it actually depends on the orientation, and it actually has different signs at different orientations. So it means that all the portions of the spectrum which relate to the perpendicular part, they go to the negative part from the Larmor frequency, and the parallel one goes to the right. And if we calculate the spectrum intensity that well, basically, this is what we see. So this is the perpendicular part, and this is the parallel part, and they're well separated. And we were very excited about this when we found out, because it promises us a very high enhancement of the resolution of Anders. So there would be a possibility to determine longer distances. So yeah, this is what I just said. And yeah, this is what we did. So we took the samples of two proteins with longer gadolinium fluorine distances. This is the spin labeled ubiquitin. This is the GB1. And we did the experiments with the help of Alex Schneck and Leonid Rapatsky in Mülheim, in the EPR center. And so if you observe the spectra at the central transition, So here you see the slightly resolved doublet, and here you don't see no resolution at all, any resolution at all. But when you go off the central transition, actually, you can enhance the resolution very much. And especially, this is nice here, because here we don't observe any resolved doublet in the central transition. So this helps us to measure, to be more sensitive to the long distances. But this is not the end of the story. Actually, for this story, this is just the beginning, because when we recorded this spectra of the fluorine Endor, we found out, to our surprise, that depending on the field position where we're sitting, where we're recording the spectrum shape looks very differently. So look here at the position A, at lower field, we see a lot of perpendicular transitions, but almost no parallel. And then when we go higher in field, like for example, when we get to this position H, then the situation is the opposite. We only see the parallel parts of the powder pattern and don't see the perpendicular part. So remembering of what we said, okay, here is the perpendicular, here is the parallel. So we evidently see the orientation selection here. And back then, just to interpret this, we used a phenomenological approach. So we just said, okay, let's stay in the frame of reference of the magnetic field with respect to the electronuclear pairs. And let us use the amount of the transitions, amount the orientations excited at each field position as the fitting parameters. And this allowed us to produce the good fitting of the spectra and determine the distances, which was important for us back then. But this approach doesn't actually provide us with any structural information. Yeah, so apparently the spectrum contains some information about the relative orientation of the gadolinium label, and means about of the zero field splitting of gadolinium with respect to the gadolinium fluorine vector. But for this, we just neglect this information. We just use it like as a fitting parameter and and we're not able to get it. So let's try and figure out how we can actually use this information. So the strategy that we would employ is as follows. So let's suppose that we have a gadolinium chelate, and we position, just by synthetic approaches, the fluorine atoms in different known parts of these chelates. So we attach a fluorine moiety next to this gadolinium chelate. So we have the fluorine 1 with some coordinates, either Cartesian or polar, and we have the fluorine 2, not necessarily in the same molecule. Actually, we use the two different molecules for fluorine 1 and fluorine 2. And then we actually fit the position of the principal axis of the zero field splitting that would match the obtained orientation of these fluorine atoms. And so here, for this fitting, we have the 4 known values, which are these angles, these orientations. And we have only 3 fitting parameters. So we want to understand what are the Euler angles of the zero field splitting in the molecular reference frame. So these were the actual molecules that we use. You see they have the fluorine in different parts of the molecule. So here it's attached directly to the pyridine ring. And here we attach it through this hinge. So basically we have fluorine 1 and fluorine 2 here and here. And on the first part of this work, of this spectroscopy, we need to analyze the EPR spectra. So as I have said, we would prefer analyzing the EPR spectra using the independent Gaussian distributions of the parameters D and E, or the principal axis of the zero field splitting frame. And to make our fit more stable and to make it more reliable, we jointly simulated spectra recorded at different temperatures, in the temperature range when the spectrum shape changes a lot because of different contributions of the different transitions. And we found out that we had the Gaussian distribution of the parameter D with this width, the Gaussian distribution of the parameter E with this width, and this is equivalent to saying that dx, dy, and z have the Gaussian distributions with this width, which were actually more or less the same. But what is important, that from this simulation, we can predict, we can calculate, okay, at each field position, when we're sitting here and here and here and here, what is the amount of orientations, which is of different orientations of the zero field splitting tensor, which are excited at each field position. So here in the position A, we mostly excite this belt towards the z-axis. But then when we go closer to the center and then when we go to higher fields, then we actually excite more the orientations on the plane. And so we can calculate this, predict this based on our EPR spectral simulation. So what we do now is that we plug in this data into the simulation of the Endor spectra. So let's look at the Endor spectra for the two molecules. Here, we recorded a series of Endor spectra. Actually, we recorded more, but I show some of them just for clarity. So we clearly see the orientation selection pattern here. So let me explain to you the spectra. First of all, when we're sitting on the central transition, we just see the Page doublet. Here, we can see it. When we go off the central transition, we can see some portion to the left from the Larmor frequency and some portion to the right. So the portion to the left is our perpendicular transitions corresponding to different electron spin manifolds, -½ -3½ -5½ and -7½ and the same we can see in the parallel domain here, but here the spectra are less resolved, and the same we can see for the second one. So we can see -7½ -5½ -3½ -1½ and of course the population of different levels is different at different field positions because we excite a little bit more or less of different transitions, but we can clearly see that we have the orientation selection. We see that at lower fields we excite mostly the perpendicular transitions, orientations, and at higher field we're exciting mostly the parallel ones. And by simulation this spectra we can actually determine the angles. So these gamma and rho are the angles that I show you that determine the position of the gadolinium fluorine vector in the reference frame of the zero field splitting tensor, just like this. So here we have a gadolinium, and here we have, let's say, this reference frame connected to the zero field splitting. So the fluorine in the complex 1 has these angles gamma rho, and it means that it is positioned here. And the fluorine in the second one has the gamma of 90 and the rho of 72, and it means that it's positioned somewhere here. So it would be very nice, but there is one more complication. So the complication comes from the symmetry. So the fact is that the zero field splitting spin Hamiltonian has orthorhombic symmetry, and it is expressed in the fact that when we observe Endor spectrum at each position, we have actually the same probability of exciting these orientations or these orientations or these orientations or this orientation. So it means that we are actually not sensitive towards the sign of our coordinates. Yeah, like the plus and minus are the same. The reflections around all the coordinates planes are the same. So it means that the first fluorine is not necessarily here with respect to the gadolinium. It can also be in 7 different positions, which are here, other positions. And the fluorine 2 is not necessarily situated here, but there are actually more positions where it can be located. And then if you look at the possible variants of the gadolinium fluorine 1 vector, gadolinium fluorine 2 vector, is it this pair of vectors or is it this one? So which one is that? So to figure this out, we can actually have one more hint. So we have one more piece of information. We know the structure of our model. So we have the structure, and of course we have the optimized structure, and we know its geometry. And from geometry, we know that actually the angle between the fluorine, gadolinium fluorine, fluorine 2, so like the angle between these two, is fixed. It's like around 55 degrees. So it means that, for example, this combination, like the purple one, it does not work. So this, taking this into account, basically leaves us with only 2 possible variants, how this this arrangement can be situated. And so there are two variants which agree equally well with the Andor spectra. And so we cannot distinguish between them. Let's look at them. So in the first one, we see that the y-axis of the zero field splitting is pointing parallel to the gadolinium, this nitrogen which belongs to the pyridine group, this one. And the z-axis is perpendicular to this plane, which is created by these 4 nitrogen atoms. So here are the 4 nitrogen atoms, and they create a plane, and one of the principal axis of the zero field splitting is parallel to this. Or, and we don't know which variant is true from the data that we have, we cannot determine this. So the second variant also is that the y-axis is oriented along the gadolinium nitrogen atom, which is in the pyridine ring, and the other axis, but here this is x, here this is z. It turns out to be perpendicular to this n plane. So basically, we get two variants, and we cannot distinguish between them using just the data that we have. So these two variants are only differ from each other by the names of the axis, yeah. So how like which one is z and which one is y. So we know where they point, but we don't really know which is which. But this restriction is not fundamental. Actually, we can think of an experiment that would distinguish between these two variants. And actually, this experiment is something that we're running now. So there is this water molecule here. You can see in the first coordination sphere of gadolinium, there is one water molecule. And we can measure the Andor from these protons on this water, of the deuteriums if we're in the deuterated sample. And then the orientation of the selective Andor from these hydrogens can actually tell us which of the variant is true and which is not. I'm still running this measurement, so I cannot tell you which. So now I will hang you with the two variants. And the same thing holds. So like we used another type of the gadolinium chelate, which is the PYMTA chelate. Slightly different, and we're using by the same technique. So we record the EPR spectrum, we model it, also of course the temperature dependence. We determine the D and E parameters and the distributions of them. We see how much of each orientation of the zero field splitting is excited at each field position, here, 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 and here. And then we use this data to simulate the EPR spectra, the Andor spectra from the fluorine. So here the fluorine is a little bit closer, and here it's a little bit farther away. And the orientation selection is not as strong as for the GO3A, but it's still, you can see it, especially with this variant. And as with the previous chelate, we get the two variants. So we obtain the principal axis system of the zero field splitting tensor, and we're still unsure about the exact indexing of the axis. So here we know that one of the axes of the zero field splitting is directed towards the gadolinium N axis, and the other two, they are sort of diagonal to the plane of the molecule. And here is the same, but just the axes are different. So the z-axis is directed towards the gadolinium N vector, and the other ones point upwards and downwards. So which one is true is a question that we are trying to experimentally answer now. But there are certain more questions that we should ask here. So the first important question is how valid it is to assume that all of this distribution of the zero field splitting parameters of D, E, X, Y, Z. So how valid is the assumption that the orientation of the zero field splitting is always the same or almost always the same? So basically all of our modeling, all of our simulation is based on this assumption. And so the second one is how well the zero field splitting orientation, which we found, can agree with the calculation. And I have told you that trying to predict the zero field splitting parameters of the gadolinium chelates from the first principles is actually quite a difficult task, and we don't aim at this, but we can use a simplified model. So what we can do is we can use the superposition approximation, which is known for these chelates. It basically says that if we have gadolinium and it is surrounded by ligands, each ligand carries a, well, let's say a point charge. And we can find this point charge by very simple simulation. So then this combination of these point charges, they create the ligand field around the gadolinium. And in general, we can assume that the geometry of these ligand fields of the geometry of the, well, actually, this is the electric field gradient tensor of these point charges, is the same. So the principal axis system should be the same as the principal axis system of the zero field splitting. Well, let's say to the first order effects. So what we do, we use the MD simulation. So like we run an MD simulation of a chelate. Here we obtain many different conformations, many different configurations. Then for each of these configurations, we use the point charge approximation to calculate the electric field gradient tensor. Then we diagonalize it and we look at how it is oriented. Where are the principal axes of this? And so here are the results. So here in the center, I'm showing you one representative structure of how the principal axis of the electric field gradient tensor are aligned, X, Y, Z, and schematically we get the same that we got from the experiment. So one of the axes, so here is the x-axis, is directed along these gadolinium nitrogen atoms, and the other one, this one, is perpendicular to the n plane. And we can quantify this. So here the angle alpha is the angle between the gadolinium pyridine bond and the x-axis of the electric field gradient tensor, and it has a distribution here shown in green. So we see that, of course, there is a variation. It varies maybe from 15 to 45 degrees, but the variation is pretty narrow. And also we can look at another angle, which is the angle between the normal to the n plane and the z-axis of the zero field splitting. So we take these atoms, we point a normal and see how it deviates from the z-axis. And this is the purple distribution, purple histogram. And we see that it's almost constant. So like it has very narrow distributions. And so here I show you these angles that the angles that we got from the EPR. So also we see that one of the axes has very, very small deviation from the NNN normal, and the other axis, the green one, is around like 20 degrees from the gadolinium N vector. So these things like the orientation of the principal axis of the gadolinium fluorine of the gadolinium chelate are more or less well predicted. So what we see from the distribution of the principal components of the electric field gradient tensor, we can see that the distribution is not as large as the distribution of the zero field splitting parameters. Well, this can have several reasons. Like first of all, probably we didn't span the whole of the conformation space using our MD simulations, although we made effort to. And of course, the second thing is that, as I have told you, the zero field splitting of gadolinium does not depend on the electric field gradient to the first order. So like these all are the second order spin orbit coupling effects. So actually, the actual spread of the zero field splitting parameters can be larger than the spread of the electric field gradient parameters. So yeah, and here more or less the same we get for the other label, for the PYMTA gadolinium. And we can also see that, yes, the distribution of the principal values of the EFG tensor is not as high as the zero field splitting, but the geometry we pretty well reproduce. So here we have the two angles, and the dashed line and the solid line is just, it corresponds to different variants that we cannot distinguish, which I told you before. So you can see that both of them are actually in the agreement with what we get from the simulations. So okay, so we can say that we are able to determine the orientation of the zero field splitting axis in the molecule with everything which has been said. But how can we apply this? And now I will show you how we can actually use this data to interpret the spectra recorded for the proteins. So again, I show you the data for one of the proteins is a GB1, and here it has the gadolinium label, and here it has the fluorinated tryptophan residue. So the thing that here, as with the previous measurements, at the lower field, we have mostly the perpendicular transitions in the ender, and here we have mostly the parallel ones. And it basically means that one of the gadolinium to fluorine vector is aligned along the y-axis of the gadolinium label. We figured out that the y-axis corresponds to the gadolinium attachment, like gadolinium pyridine group of the label. So here is the structure that was determined actually from this data. So from the distance between gadolinium and fluorine, and from the orientation between of the gadolinium and fluorine. So let us look at another variant, which is a ubiquitin, also spin labeled. So here we have a different picture. We have at lower fields, we have mostly the parallel transitions, the orientations. And at high field, we have mostly the perpendicular ones. And basically what it shows us is that the vector that connects the gadolinium and fluorine here, well, here we have the three fluorine, but they're close around. It is oriented along another axis, like here. We figured out that it will be the x-axis of the zero field splitting. And so we can actually position it. So then let us look at this computational experiment. So of course, we know that when we attach a label, the spin label has a distribution, a conformational distribution. So it there are a lot of conformations which can be obtained. And we usually use these programs. So this one was calculated using the MTSL wizard. We use this program actually to compute all possible conformations of the spin label with respect to the protein. So then what we get, so we can take every one of the conformations, every one that we obtain, and we can see how the axis, so like first of all, we can see the gadolinium and fluorine distance here, and it has the distribution, the calculated distribution. But also these angles, the gamma and rho, which determine the gadolinium fluorine vector orientation in the zero field splitting frame, we can predict it on the basis of the of this geometry. We can compute it. And well, this line is the one that we get in the experiment, also the distance, but this is a distribution. And then it turns out that if we just take this distribution and plug it in the simulation of the Ender spectra, it will produce us the spectra, which are the red ones, the simulated ones, which actually don't agree very well with the experimental data. So they show much less orientation selection. And it basically means that the predicted span of the conformational mobility of the label is actually much more than we actually observe in the experiment. So in the experiment, the label is much more rigid than we would expect just from these simple in silico considerations. And here I demonstrate this in another way. So I only show here the gadolinium positions. So the small spheres is the ones that are predicted by the in silico labeling programs. And the large spheres are the only ones that are consistent with the Endor data. And you can see that actually the conformational space, which is spanned by the label here, and especially here, is much narrower than we get from the experiment, which is much narrower than what we can predict. So supposedly, the application of this additional information that we get from the orientation selection actually gives us more information and can be interpreted in structural biology. So I think that it's now time to go to conclusions. Well, basically, first, experimentally, we observe very clear orientation selection in the Endor spectra of gadolinium chelates. And it means that the actual zero field splitting axes are oriented in a certain way in the gadolinium chelates, so they are not completely distorted, they're not completely disoriented, despite the distribution of the principal values is broad. And so we can basically determine this orientation of the zero field splitting axis with respect to the molecules. And they agree well with what we predict from this simple, naive ligand field theory model. And of course, we can use it in the structural biology measurement. So the last thing that I want to show you is that basically recently we also published a work which is ideologically close to what I have shown you here. So we worked here with this chemically modified cyclodextrin, which has the chemically attached DTPA ligand with a gadolinium inside. And inside this cavity, so it's like a cyclodextrin is like a molecule with a hole, like a donut. So inside it, a fluorinated molecule can come. And because of the geometry of this chelate is very, very much distorted, it has quite broad central transition. And here, even on the central transition, we can actually see the orientation selection. You see that when we observe here on the lower part, on the lower field part, then we see a lot of parallel orientations. And here we almost exclusively see parallel ones. We're sitting here. And so here in this work, as in what I have, I tried to explain you now. So we analyzed the positions of this fluorine and managed to find out how the guest molecule, like the molecule that goes inside this cavity, how it is oriented with respect to the zero field splitting of gadolinium. So it's published, you can look it up. And so now the thank you slide. So I would like to express my gratitude to everybody who took part in this project. And of course, Daniela, who is the engine of this, and other people at the Weizmann Institute, Manash, Irina, Veronica, Elad and Amnon, and Alex and Leonid, who helped us a lot with the low temperature measurements of Endor, and Venkai and Angela, who provided us with fluorinated proteins, and Su Chen, who provided us with the spin labels. So everyone whom I asked for help, and the organizers of this meeting for the invitation, and of course you for the attention. Thank you.
All right, thank you very much, Alexey, for your talk. Now the floor is open for questions, so I encourage the participants to unmute themselves and ask the question directly to Alexey. Oh, we have a question in the chat from Fred. Slide 21. I read it out loud. So on slide 21, can you explain what were the signal in the high frequency domain? Is it proton?
So I think I understand what you're talking about. Is it 21? So I think you're talking about this. So yes, this is the protons, because here the fluorine gadolinium distance is quite small, so the splitting is large, and this is why the part of the fluorine spectrum actually intersects with the protons. So yes, this is the protons.
I have a very naive question. Like, what is the maximum distance you can measure between gadolinium and fluorine? Maybe you said that. And how does this compare with nitroxide fluorine, if it's different?
So with the enhancement that is provided by the high spin of gadolinium, we managed to go as high as 15 to 16 angstrom, so 1.5 nanometer. We estimated that we can go higher, up to maybe 2 nanometers. I know that, so first of all, there is a work from the group of Nick Cox. They're determining the distances by integrating the spectrum, because the Endor efficiency depends very much on the distance. It's actually the intensity of the spectrum. Spectrum depends on the distance in the 6th power. So this is why, by determining the absolute intensity of the spectrum, you can also judge the distance, even if you don't see the splitting. So they claim to go up to 20 to 25 angstrom. And recently there was a paper out from Marina Benati's group, who I think that Luca will be talking about this in a few meetings from now. And so they used basically they were refocusing the nuclear dipolar couplings to remove, basically to diminish the line width to the extent to the limit. And I think that they can get up to also 20, 25 angstrom. So, well, I think that 20 to 25 is a good estimate of where you can go.
All right, thank you. Any questions from the audience?
Yep. Can I ask one question?
Sure, go ahead.
Yeah. Of course.
Alexey, it's a great talk.
Thank you.
My question is, see, for example, okay, all the Endor experiments you carried out at low temperature, see, because you are looking at the structural aspects of the gadolinium complexes with the proteins. So what about, whether the rate of cooling will affect the structural aspects of this gadolinium complex and the proteins orientation? Because if you cool the samples at 2 different rate of cooling, whether that has any influence on the structural aspects.
So I think that it should. First of all, so it also depends on the cryoprotectant that we use. So basically, it depends on the temperature at which the mobility of the spin label gets frozen. So when we were working with the small molecules, just the conformation space that has to be spent by the molecule is very small. So basically, even at moderate cooling rates, we get more or less equilibrium conformational space. However, of course, with the proteins or with the nucleic acids, we have to take care about the cooling rate. And actually, so as you have seen, the Endor is a short range, like shorter range technique that provides the information about the shorter distances than, for example, the DIR and the EPR dipolar techniques. So basically, it is more sensitive towards the conformational distribution of the label. So then, in principle, we can see it, we should see it. Also, sometimes we see that when we cool it with different rates, we see the difference in relaxation times of the spin labels. But I think this more relates to the structure of the glass that the quality of the glass that we obtain. So yeah, I think that when we're talking about the structural studies of the real systems, of course, it can be sensitive.
Thank you. My next question is now, at the same time, if you change the solvent, different buffers, they may also play some role. So in that case, we may get some more information. If you change a buffer, then you get some more structural aspects. So
I think yes, it depends. It depends on the system in question. Like if we're talking about like the specific protein, then probably we really can answer these questions. The thing is that we should take care doing these measurements that we are actually learning something about our protein and not about the spin label, right? So because the spin label is a tool, it's not the objects itself. So this we have to keep in mind.
Thanks.
Thank you very much.
Yeah.
All right, we have a question in the chat, or from Songi. So basically, she's is a commenter and question, and then she's asking about the possibility of doing I-field ender at low temperature when only the 7.5 is polarized, -7.5. So I think the bottom transition.
Basically, this is the. Let me show you here. This is the regime where we worked here. So you can see that at the low temperature, around 2K at the W band, and of course at the higher field, we can go higher in temperature with this. We have almost exclusively observed the -7.5 to -5.5 transitions. And of course, if we go even lower, well, it is restricted, it is limited of how low we can go. It's limited by our cryostat, basically, by our system. But then if we go lower, then we can get even more polarization. So the shape of the spectra will stay the same. So this here, I think that to simulate this, you actually don't need to include any other transitions other than -7.5, -5.5. So then, okay, we get more polarization, we get more signal, we get more SNR, but also, we go into different spectrometer, we get smaller samples. So this is also a trade-off.
Okay, thank you. Any other questions from the audience?
Yeah, can I ask something?
Yeah, go ahead, Andres, please.
So you showed this example with the protein where you looked at the flexibility of your label, and then your data said that there's low flexibility, but the modeling said there should be a lot of flexibility. So do you have any idea why apparently the label is less flexible than what the modeling says? So is there any physical explanation as to why it's sort of, rigid, apparently?
So, let me go there. Well, in general, the modeling that we used was quite naive in the sense that so this is this MTSSL wizard type modeling that actually allows all conformations, like all possible conformations, which exclude the clashes between the structure of the protein and the structure of the label. Of course, in the real life and the real solvent, there are other contributions. First of all, not all rotamers have the equal energy. Then different rotamers, they exclude water differently, for example. So there are also entropy effects, and some of them can be more favorable and the others can be less. So an interesting case is this ubiquitin that we observe. So here the label seems to get inside the pocket. So like here the protein forms a certain pocket which is like a bit hydrophobic. So for some reason the label is mostly situated here next to this hydrophobic pocket instead of obtaining all of these conformations which are in principle possible, but like we mostly see it here. So probably these are some specific interactions or maybe hydrophobic interactions here.
And is there, does it align with some other, because I know in your group you did a lot of experiments with gadolinium, and maybe does it also align with some Peldor experiments or?
So the Peldor experiments, We haven't done the Pelder experiments with the same label and positions of ubiquitin. Probably can be done, but you are just less sensitive to these small distances in Pelder, so probably we just will not see this. But for this variant, we clearly see from the Endor experiments, and like we have seen this for a long time, that that the distance that we obtain from Endor is less than the one that is obtained from the simulation. This is not exclusively true for gadolinium spin labels, though. So like when we put a nitroxide spin label here in the same system, in the same mutant, we also see that it inclines towards smaller different distances. The other possibility that we cannot discount here is that we're using the structure of the fluorinated molecule, which is known from, like we assume that this is the same as in the crystal structure of this ubiquitin. So in general, when we fluorinate this molecule, especially if it has the mobility, it has the possibility to go, then it can actually change the position, the fluorinated label itself. And here to figure out what is the case, of course, we need to have data from multiple labeling sites, so to compare and to see whether this is the flexibility of the label or of the spin label or the flexibility of the fluorinated moiety.
Thank you.
Okay, we have other two questions. Let's go with Paolo first. Can go ahead.
Okay. Hi, Alexey. Nice,
Hi, Paolo.
very inspiring talk. I was just wondering if you also tried to use DFT for the zero field splitting orientations to correlate this, or how bad were the calculations?
Well, very bad.
Very bad. Okay.
Really, really very bad. Like just the principal values were completely off. But also, I'm not a computational chemist, so probably I was not doing everything all right. I think that I did the CAS-SCF computations. We discussed it. And so even at the convergence was a disaster. And even when it converged, it produced the results which did not make much sense. So
okay,
with my hands, with my abilities, I don't think that I can do this.
Okay. Yeah, I was curious about this because usually I didn't have bad experiences with the orientations. I mean, for the absolute values, of course, but
yes,
but for
like
hyperfine and G and G values, never
but
tried with
gadolinium is
zero.
tough. Gadolinium is tough because well, because of all of these things.
Okay.
You have to account very very well to the excitations, like to the excitations with a non-zero orbital momentum. So and then how well you do this, it depends on the level of your theory, on the trade-offs between different approximations. So I just think that it's really hard. In the literature, there are a few works for very simple compounds, very symmetric ones, where they predict the zero field splitting values. I think even like for the echo complex, mostly they use, but they also use, I think, 1 chelate. And they predict well the principal values, but the orientations, like probably they predicted well, but we don't have anything to compare with. So
I see.
especially with the echo complex, it just does not exist.
Okay.
Thank you
Thanks.
very much. Thanks, Paolo.
Right. We have one question in the chat from Enrico Salvadori. So he asks, can you elaborate a bit on the link between zero field splitting and EFG? How general is this approach?
So the thing is that if you have the ground state with the orbital momentum, with a non-zero orbital momentum, then the zero field splitting is directly proportional to the EFG through the spin orbit coupling. But when we're talking about the gadolinium state, which has the L equal to 0 state in the ground state, we have to include the excited states. So then the excited states with different orbital momentum can contribute differently to the zero field splitting. So, and this will be the second order effect. So the effects are very small. But basically the symmetry of the ligand field is the only symmetry that is actually important for this. So like the EFG should be very good, should be good at predicting the geometry as far as I understand. And it should be quite lousy at predicting that. So it just like cannot work because it works at the first order, and in the first order there is nothing with gadolinium. So it's unable to predict the values. Enrico?
There is some background noise. Not sure if...
Alexey,
Yes.
I have one more simple question. What
Of
will
course.
happen? What will happen if we replace gadolinium with high spin manganese, cobalt, or iron? What do you think?
Well, a lot of things will happen. First of all, the ionic radii of these different ions are different, so the whole structure of the chelate will be different. And well, then of course there are d electrons there, and the d electrons will try to align the ligands around them according to the geometry which is preferred by the manganese. So like, let's say the octahedral, or which is preferred by, so there are studies of manganese pi-YMTA, so with the same chelates as we used here, but with a DIR. And in DIR, I think they predict the distance as well, but nobody looked at the zero field splitting of these compounds. So I don't know. The honest answer is I don't know.
Oh, thank you, thank you.
But like it will change a deal of changes will probably also in the structure of the label.
Thank you, thank you.
Right. Any other question, last minute questions? It was a pretty intense Q&A. Okay, looks like we have no more question for Alexey. Alexey, thanks a lot for your talk. Thank you all the participants for the Q&A and the stimulating Q&A session.
Thank you very much, and thanks everyone.
Yeah, I'll see you in 2 weeks' time, and Alexey already advertised our next talk by Luca Sila from Marino Bennati's group, again on dipolar spectroscopy, hyperfine spectroscopy. All right, Alexey, can you stay a few minutes
Yes, sure.
after? Okay, great. I'll stop the recording.